Let's take a look at this problem. It says a metallic bar, 300 millimeters, and let me use this one here. So 300 millimeters, 100 millimeters, and 40 millimeters. Those are the dimensions of this bar that I have depicted here. It's subjected to a force of 5 kilonewtons. Tensile, 6 kilonewtons tensile, this one, and 4 kilonewtons tensile in this part, along x, y, and z directions respectively. So this is kind of a little bit of a weird representation of the x, y, z system we are used to, but it's done in this way so we can kind of see the whole dimensions clearly. It says determine the change in the volume of the block, take the Young modulus to be this one, and Poisson's ratio to be this one. Excellent. So what is the change in volume? Well, we discussed that when we have forces or loading on a body, the only stresses that are going to cause change in volume in a body are those normal stresses created by those forces or loading. So, and the change in volume is represented by, I'm going to write here in blue, this formula. So the change in volume actually is represented like this. Again, this is non-dimensional, it's a rate of change, so we need to give it a volume in order to determine how much was this volume change, so we need to give it a volume. The same happens with strains, remember that. So we have that this is equal to what? Well, we're going to have the effect of the elasticity module here, and then we're going to have the effect of those normal stresses. And remember how I am writing these stresses. Remember that I could write it like sigma xx or like this for simplicity. And then we have to take into account the latter, kind of the change in the other directions of those applied loads. This is why we need to use Poisson's ratio here. And remember, I'm calling mu here, but also I could have called it this nu. It could be used interchangeably in the literature, so be mindful of that. So what is left doing here? Well, just calculate each one of these stresses in each one of these phases. And remember, this is an element, and it's pretty similar to the infinitesimal cube we have done. In this case, well, we have larger units here, but it's not written here, but no, we know that in this kind of in the country phase here, we have another load applied here, yeah, because this is static equilibrium, so this has to be here. Awesome. So again, what is left to do is just calculate each one of these stresses here, this one and this one, substitute the values, then multiply times the volume and the t. So, well, we need to calculate 4 things: volume, stresses, applied, put it in the formula, and determine the change in volume, which is this dV. That's it. That's as simple as this. So let's do it. First, let's calculate the volume, just to get rid of that part. So the volume is going to be, I'm going to use as units newtons in force units, and I'm going to use millimeters in length units. So volume, I'm going to leave it like this, and it's going to be just from smaller to largest. 40 millimeters times 100 millimeters times 300 millimeters. So the volume is going to be, I have the calculator right here. I'm going to write it, kind of give it a name, volume. 40 times 100 times 300. That's going to be, how many zeros do we have? 1, 2, 3, so 1.2 million. And I could write it like this. So about 1, 2 times 10 to the power of 5 millimeter to the power of 3. And this is one result I'm going to need later in the resolution of the problem. Then let's calculate stresses in x. And we know the stresses in x are the force applied in x, and then the area of this where this stress is applied. So the area is going to be this one here. So, and it's determined by the length or the length in the y direction and the length in the z direction here. Yeah. Then I can write it actually there. So it's going to be distance in y times the distance in z. Then actually let's put it like this. See, that's going to be equal to 5,000 newtons, to get the units I want to use. And then I'm going to have here y, which is 100 millimeters, times z, which is 40 millimeters. Then this stress is going to be how much? Let's go to the calculator. This problem is pretty trivial, so it's going to be 5,000 divided by 100 times 40. And that is 5 quarters, and that's 1.25. Here, 1.25 watt newtons per square millimeter. and this is another result I'm going to use. So let's move forward with then sigma y, and this is going to be the force applied, the direction, and then what are the areas we're going to be intervening here. So it's going to be distance in z, distance in x. So I'm going to have this x times z. That's going to be equal to 6,000 newtons divided by, open here, so x is 300 millimeters, times, this is not plus, this is times. Yeah. Oh, this kind of makes sense. Let's put it like this, like a dot, because it gets confused with the x there. Yeah, sorry about that. And this is going to be times and z, which is 40 millimeters. I can leave it here. Okay, no problem. Which means that sigma y is going to be what? Let's go to the calculator. It's going to be 6,000 divided by 300 times 40. And that's 1/2, and that's 0.5. 0.5 newtons per square millimeters. There you go. Now finally, we need to calculate the stress in the z direction, or on the z face, and that's going to be the force applied there, then divided by the area where it's acting that force, which is this one. So this is y and this is x. So I can write it out here, kind of x times y. And that's going to be how much? 4,000 newtons divided by x is 300 millimeters times how much is the other is y, and y is 100 millimeters. Which means that this stress equals to what? Let's go to the calculator. Let's call it then, it's going to be 4,000 divided by 300 times 100. That's 2 divided by 15, which translates into this. 0.13 newtons per square millimeters. And this is another factor. And I already got everything to do it. So let's come back here and say, well, you know what? The change, let's use this color to differentiate. So change in volume is going to be what? Oh, I love this software. So it's going to be dV equals to what? To V, because we are taking this dude here that we already calculated here and then putting it to the other side of the equation. V divided by then E, then that multiplies, let me just rearrange the formula here, plus this one times this, then dV, I'm going to substitute the values. It's going to be 12 times 10 to the power of 5 millimeters to the power of 3 divided by what? By this 2 times 10 to the power of 5 newtons divided by millimeters square. That multiplies these three stresses, normal stresses, and again, I need to repeat it, normal stresses are the only ones who change the volume of the body. Shear stresses are the ones who deform the body, that deform the body. So I'm going to write like this, 125 plus 0.5 plus 0.13, and this is in newtons, millimeters square, and this multiplies what? 1 minus 2, that multiplies Poisson's ratio, which is this one here, and this is going to be 0.25. Then this change in volume is going to be equal to what? Let's go to the calculator. It's going to be then V divided by E, and E is 2 times 10 to the power of 5 times the sum of the normal stresses, which are A plus B plus C. I'm just using the same reference. The results already gotten here, so that's why I can write it like this. And then this is going to be equal to 1 minus 2 times 0.25. And that is 113 divided by 20, and that's awesome. This is going to be 5, here it is, 5.65 watt units. So let me check. So I have, check this, so I have that this cancels out with this, and the only remaining units are millimeters to the power of 3, which are volume units. So this is going to be what? millimeters to the power of 3. And this is the answer to this problem. Now to summarize what we did, so we did a graphical representation of the problem. If you are able to see it without doing this graphical representation, it's fine, no problem. Then we know that only normal stresses change volume, so that's why we can use this formula that relates the change, simultaneously change on those 3 sides or 6 sides, put it in that way, well, 1, 2, 3, 4, 5, yeah, 6 sides. And we just need to calculate how much is the volume, which is a piece of cake, how much are each one of those normal stresses, which we use a normal or traditional definition of what a stress is. And then we just substitute everything in this formula and get how much is the value, which is this much. Meaning that by applying these 3 forces simultaneously on those faces of that bar, we're expected to produce this volumetric change, which is positive, which means it's going to expand. So is that large, is that small? Well, we don't know. It depends on the application. And this is the end of the problem. It's pretty simple again, and then it reflects on the thought or premise that only normal stresses change volume. See you in the next problem.